Hello everyone! Welcome to the final lesson of this course, Lesson 7, Areas Between Curves. To find the area, a of x, between two curves, where f of x is greater than g of x on the interval a, b, determine the integral seen below. Basically, here's what's happening. When I say when f of x is greater than g of x, I'm just saying that f of x is above g of x. It's higher up, right? It's a larger values of y for every value of x. So the way that we find the area between them, well, think about it. First we have the area completely under f of x. So that's everything down to the x-axis. And if I want to get just the area between them, all I have to do is take that whole area of the top function to the x-axis and subtract the area under the lower curve. So that's why the area of x is the integral from a to b of f of x minus the integral of a to b of g of x, where f of x is the function on top and g of x is the function below. All right, let's do an example. Find the area of the region bounded by the parabolas y equals x squared and y is equal to 2x minus x squared. So first thing I want to do is I want to be able to draw this so I can tell which function's on top, whether they intersect at any point, all of those kinds of things. So let's start with y is equal to x squared. For y is equal to x squared, well, this one's actually kind of nice. We know what the x-intercept is. It's a really simple parabola. We know how to sketch that. The x-intercept is going to be 0, 0. It's the standard parabola. The second one is a little bit harder, but not a lot. This one, we just have the factor, right? So we can find the x-intercepts by setting it equal to 0, and we can rewrite this as negative x times x minus 2, right? Just factoring it. So what we get for our x-intercepts are 0, 0 again, and 2, 0. Okay, so I've got all my x-intercepts. Let's sketch this thing. So I'm going to start with my y is equal to x squared. That one's really nice and easy to draw. Whee! That was a terrible parabola. That is a slightly better parabola. All right, and the second one, we know it opens down because it has a negative x squared term. And we know that it has intercepts at both 0 and at 2. So here's 2. And we also want to find one other thing about these. That's their intersection. So we want to check if there's any place where the two curves intersect. So to do that, we just set the functions equal to each other. When is x squared equal to 2x minus x squared? So we move everything over to get it equal to 0, because that's how we do these things. And we get that 2x squared minus 2x is equal to 0, which means that 2x times x minus 1 is equal to 0, which gives us intersections. So we have intersection points at x equals 0 and x equals 1. All right, so they're going to intersect when we draw this here. That makes sense. They both have the same x-intercept there, so clearly they'll intersect there. But they're also going to intersect here at 1. Somewhere at 1, so around here, let's say. So the parabola I get is this. So if we're looking at, hey, where do they intersect? Well, they intersect in this really small area right here. Sorry, not where do they intersect, where do they overlap? What is the region bounded between them? That's the region bounded between those two curves. That is what I am ultimately looking for. That's the area I'm looking for. So just to be clear, this is y is equal to x squared, and it's always good to label your curves when you draw them. Y is equal to 2x minus x squared. Perfect. Okay, so now we want to find our area. So to find our area is going to be the area of the curve above minus the area of the curve that is below. Okay? So this is going to be the integral from 0 to 1 of 2x minus x squared dx, because if you look, 2x minus x squared, that is the above curve. That is the curve on top. The blue one is above the red one, all over that domain. Then the area below is going to be the integral from 0 to 1 of x squared dx. Okay, now just like we can split up an integral when it's a bunch of functions added or subtracted together, we can also put them together. So we can rewrite this as the integral from 0 to 1 of 2x minus x squared dx. So I'm just putting my pieces together. That's one of our integral properties, which nicely reduces to 2x minus 2x squared dx. Now we just take our definite integral. This is going to be 2x squared over 2 minus 2x cubed over 3 from 0 to 1. The 2's delightfully cancel out, and we are left with 1 squared minus 2 times 1 cubed over 3 minus 0 squared minus 2 times 0 cubed over 3. Well, that one wasn't so bad. This is going to be 1 minus 2/3 minus 0, which is just 1/3. So the area is 1/3 unit squared. Told you it was small little area, just a third of a unit. All right, and that's how you find the area between two curves. Let's do one last example, one final example for your high school calculus course. Whew, so close. All right, what do we do in a situation like this, where they intersect each other over the domain you're looking at, where they actually switch positions, where the curve that was on top moves to the bottom and the curve that was on the bottom moves to the top? So if f and g intersect at some point, x equals c, on the interval of ab, so that f of x greater than g of x turns into g of x greater than f of x, it switches which one's on top, at the point x equals c, we just split the interval and do them separately. So in this case, this would be our c, right? This would be our x equals c. That's the place where we're going to split it up. Right now, up here, cos of x is the one on top, but over on the other side, in area 2, it switches and sine is on top. So we'll just do it in pieces. So the first thing we need to do, though, is figure out where that intersection point is. Now, you can probably tell where it is just by looking at the graph, but it's good to practice making sure it's accurate, and you can never assume that a graph is 100% right, although, you know, using your noodle, you can probably figure it out. Sine x is equal to cos x. Remember, we're restricted over this domain right here, so the only place where sine x is equal to cos x over the domain between 0 and pi over 2 is when x is equal to pi over 4. That's the only place that they're equal. And hey, that's exactly what we see on the graph. You can see it just by looking. But it's good that we check. Make sure you do. All right, so we're going to do these one at a time. I'm going to start with a1. a1 is going to be the integral from 0 to pi over 4, right? Because that's where a1 is. a1 starts at 0, ends at pi over 4. Of cos of x, because over a1, cos x is the higher function. It's the one that's on top. Then we'll subtract the integral from 0 to pi over 4 of sine of x dx. All right, I'm just going to jump. So we know we can combine these, so I'm just going to take their integral and put them from 0 to pi over 4. Just skipping the step where I combine the integrals. We know we're going to be able to do that anyway. So the integral, the antiderivative of cosine of x is sine x. And the antiderivative of sine x is negative cos x. This will be minus negative cos x. And then I'm going to split this up. So it's going to be sine of pi over 4. Negative negative is positive, plus cosine of pi over 4 minus sine of 0 plus cosine of 0. So what I get is sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2, minus sine of 0 is 0, cosine of 0 is 1. So what I get, words are hard, root 2 over 2 plus root 2 over 2 is just root 2. And then we subtract 1, because 0 plus 1 is, go figure, 1. So that's area 1. Let's do area 2. So area 2 goes from pi over 4 to pi over 2. And which one is on top has switched. So we're going to be taking from pi over 4 to pi over 2. We're going to be taking sine x. Now sine x is the one that's on top. They've switched, right? Y is equal to sine x. The blue curve is now above. Dx minus the integral from pi over 4 to pi over 2 of cosine of x dx. All right, so what this gives me is, again, exactly the same thing we did above. It's just now from pi over 4 to pi over 2. That's the only thing that's changed, and of course the order of subtraction has changed as well. So now what we have, the integral of sine x is negative cosine of x minus the integral of cosine x, which is sine of x. So we take that at our two major points. Negative cosine of pi over 2 minus sine of pi over 2 minus negative cosine of pi over 4 minus sine of pi over 4. Cos of pi over 2 is 0. Negative 0 is still 0, so that's 0. Sine of pi over 2 is 1, so it's minus 1. Minus cosine, negative cosine of pi over 2 is going to be negative root 2 over 2. And negative sine of pi over 2, also negative 2 over 2. Which gives me negative 1 minus negative root 2. Which of course finishes to root 2 minus 1. Hey, it's the same as area 1. It's almost like if you were to look at that graph, you'd notice that this entire thing is perfectly symmetrical, so A1 and A2 are totally equal to each other, and we could have just solved for A1 and then doubled it. Crazy, huh? So anyway, total area is then just going to be A1 plus A2, which is going to be root 2 minus 1 plus root 2 minus 1, or, just another way of saying that would just be, hey, this is 2 root 2 minus 2, just doubling it. And there we go. That's our area. And there's only one question in the homework. All right, we have finally finished. This is the last video I have to record and the last one you have to listen to from me. So give this a try, do the homework. Let me know if you're having any problems, but otherwise, talk to you soon.